Today we're going to talk about exponential functions. Going to get the definition. An exponential function looks like this. You have a times b, where b is going to be a base, to the power of x. So the difference between an exponential function and a power function is that in the power function we had x to the power of some set number, like x squared, x cubed. And this one, the x is going to actually be the exponent. So this is like an example of 2 to the x power, 3 to the x power. So that's the difference between an exponential and a power function. So let's go ahead and get some tables done of exponents. Let's do a table of ordered pairs for y equals 2 to the x power. So when we plug in 3, 2 to the negative third is 1 over 8. 2 to the negative 2 is 1 over 4. 2 to the negative 1 is 1 over 2. 2 to the 0 is 1. 2 to the first power is 2. 2 to the second power is 4. And then 2 to the third power is 8. So that's an example of ordered pairs for 2 to the x. And in a moment, we'll look at the graph of that because we're going to plot those points. But let's go ahead and compare it to the table of ordered pairs for y equals 1/2 to the x. So this is still an exponential function, but instead of doing 2 to the x, we're doing 1/2 to the x. So when we plug in negative 3, 1/2 to the negative third power is 8. Because 1 over 2 to the negative 3 means that the denominator is going to go to the numerator, becoming 2 to the third, which is 8. Negative 2 becomes 4. 1/2 to the negative 1 becomes 2. And then 0 is going to become 1. 1/2 to the first power is just 1. 1/2 to the second power is 1 over 4. And then 1/2 to the third power is 1 over 8. So notice that when our base was 2, the y values went from small to big. But now that our base is a fraction or small, our numbers are getting smaller. Okay, so here are those plotted points. So this is y equals 2 to the x power is this graph. And this is y equals 1/2 to the x power. So if you notice, these numbers seem to be approaching or kind of settling off. We call that an asymptote. Asymptote is a line that a graph approaches but never intersects. So if it looks like it's just going to go on and on and on but never really go past that, then it's called an asymptote. In both of the tables that we did for y equals 2 to the x and y equals 1/2 to the x, we had a domain of all real numbers. We could let x be anything. And because of that, our range was a set of positive real numbers. Because no matter what number we put in for x, we could never get a negative number. So our range is going to be only the positive real numbers, or we say y is greater than 0, right? It cannot, your y's have to be bigger than 0. They cannot be negative. So another thing that kind of is a characteristic of exponential function is that sometimes before the base, before 2 to the x, they put another number. Right now we're just going to call it a because it could be any number. But this might look like 3 times 2 to the x, 5 times 2 to the x. It's just another number before the base and to the x power. Okay? And what that does is that for every value of x, the y value is just going to be times that a value. And then your y-intercept is very easy to find because the y-intercept will just be 0, comma, whatever that a value is. So you don't even have to look at the graph. If you know the equation y equals, let's say, 7 times 2 to the x power, you know that your y-intercept is going to be 0, comma, 7. You don't even have to look at the graph to see where it crosses the y-axis because you know it's just going to be 7. Let's talk about reductions and enlargements because this is something that exponential functions are really good at finding. So for reductions and enlargements, we use the formula y equals p to the x, where P stands for the percentage that you want either enlarged or reduced. Think of a copy machine. When you put a piece of paper on there, and let's say you want to blow it up so that way it's big so you can see it better, that's an enlargement. Or let's say that the paper's too big and you want to fit 4 of them on one page, so you need to reduce it to make it smaller. That's a reduction. And so P stands for percentage, so it's a percent, but it is a percent that we have to change to a decimal. And then the x, to the x power, that x represents how many times you're going to enlarge or how many times you're going to reduce. So let's do an example. We're going to do 3 consecutive reductions of 75%. So our P is 75% or 0.75, and our X is 3 because we're going to do 3 reductions. So P is 0.75, and so our equation is y equals 0.75 to the x, and we're going to let x be 3 because we're going to do 3 reductions. And so in our calculators, we'll put 0.75 to the third power, and we're going to get approximately 0.422. And so what that tells us is that we can change that 0.422 back into a percent, and that tells us that if we do 3 reductions of 75%, then we have 42.2% of the original. Let's do an enlargement now. We're going to do 4 consecutive enlargements of 150%. So our P is 1.5 because we changed 150% to a decimal, which means our equation is y equals 1.5 to the x. So we're going to let x be 4 because we're going to do 4 enlargements. And our calculator tells us that 1.5 to the 4th power is approximately 5.063. Change that back to the percent, and then we know that if we do 4 consecutive enlargements of 150%, we get 506.3% of the original. Another useful thing that exponential functions is used for is compound interest. If you ever invest money in a savings account, usually they will give you interest for it, or you'll collect interest. So the longer that you have your money in the account, the more money you're going to earn. So we have a formula, and that formula is modeled with an exponential function. So remember, our definition of exponential function is mean that your x, or your variable, is the exponent, right? So for this formula, we have y equals 10,000 times 1.05 to the nth power. So the 10,000, this number before our base and our exponent, this 10,000 represents how much money you put into your account. You put $10,000 into your account. This 1.05 says that you have a 5% interest. 5% interest. The N is the number of years you're going to leave your money in your account. So let's say we do 1 year. So that means N is 1. So we'll plug 1 for N into our equation, and our calculator will do 10,000 times 1.05 to the first power. Very, very important. When you plug this into your calculator, make sure that you separate 10,000 and 1.05 to the first power. You actually might want to do 1.05 to the first power first, and then multiply it by 10,000. So that way your calculator doesn't get confused. So our calculator says that that is $10,000, $10,500. But remember, we started with $10,000. So you actually only got $500 extra money because you had already started with $10,000, right? But hey, after 1 year, $500 for doing nothing but sitting in an account, that's not bad, right? If we do 2 years, so n is 2 now. So in our calculator, we'll punch that in, and it tells us $11,025, which means that after 2 years, our $10,000 earned $1,025. What about 50 years? Well, n would be 50, right? So we plug into our calculator. Wow, it's a big number, 114,674. But remember, we started with $10,000. So the actual amount of interest is minus 10,000, so 104,674. That's how much money we earned in our interest account. All right, go ahead and try 2 through 6 evens.